Yeah, I'll be speaking about the neural correlates of geometric visual hallucinations. So, hallucinations in general are quite broad. We have these complex visuals where we see faces, places, objects, things like that. I won't be speaking about that. So when I refer to a hallucination, I'm referring to a geometric, simple hallucination. Just to gauge that we're all on the same page, show of hands, how many of you have experienced a hallucination before? Nice. Perfect. Okay, so we all know what a hallucination is. So it turns out the guy who painted this picture, he also had a hallucination. So the guy who painted it, he was called Juan Miro. He's part of the Surrealist movement. And to get inspiration, he would starve himself, and he'd get these hunger-panged hallucinations that gave inspiration to some of his paintings around this time period. So to get a picture of what Miro saw, or even to put this talk into context, let's simulate a hallucination.
Very hallucinogenic effects. But please do not be afraid, these effects usually last a few seconds. Read aloud every letter shown in the screen center. Do not make any mistake. You can look away now.
So, cheers guys. I mean, I didn't really do anything there, but thank you. Yeah. So, if your visual cortex is functioning fairly normally, some of you would have seen some movements around your visual field, some distortion. So that was a hallucination. And William James, he defines a hallucination as a strictly sensational form of consciousness. As good and true a sensation as if there were a real object there. The object happens to be not there, that is all. Obviously, the hallucination you guys experience is far from stuff we see under psychedelics. Under a high dose of psychedelics, one might see something like this. Ooh. And maybe at a lower mid to low dose, we still see patterns, but maybe just not as intricate or rich like these high dose peak experiences. But you might get something like this on a more lower dose. So this picture was taken last summer for me and my friends in the north of Italy. The guy who took this picture is a good friend of mine, Theo. Theo doesn't take psychedelics, but say if he dropped a tab of acid 2 hours ago, he may see something like this on his visual field. And maybe 82 years ago on this fateful day, Albert Hofmann might have seen this on his bicycle ride home from the lab. And in maybe 7 to 8 hours, some of you might see something like this as well. Right? And yeah, so my talk is going to try and break this down. Firstly, these patterns are not indicative of the full-blown psychedelic experience. It's far from that. It's a simplification that's just trying to understand what might be going on. visual hallucinations are quite difficult to study in general, right? The neuroimaging stuff, we see an area in the brain light up, but beyond that, we don't know what's happening. So we use models, these computational models. And it's a cheap way of doing research. We don't have to set up a study, and it helps inform new hypotheses. So that's what my talk will be based on. And a quick caveat. So a lot of early brain research came from studying visual perception, and almost every psychedelic has some sensory quality to it. But some people seem to think that this is a byproduct, an epiphenomenon to the experience. And often when we speak about these visuals, we speak about these visuals as being cool. Colloquially, we use the word trippy to describe these patterns, but the conversation stops there. And we can do better than that. By leveraging these lower level sensory dimensions, we can inform brain dynamics, therapeutics, the experience, and get a much more well-rounded picture of the psychedelic experience. And hopefully we'll address some of those gaps there. I recommend this paper by Marco Achille and Leo, which goes into the visual sensory dimensions in much more detail. So my talk will first look at how we hallucinate, the retina and the visual cortex. Then we'll talk about why we hallucinate, what's going on at the back of the head to cause these patterns. And finally, I'll bring it all together and explain what might be happening under psychedelics. So the Turkana people are a group of indigenous people that live in the northwest Amazon. And within that culture, they've got these documented patterns that are meant to represent hallucinations. Then many moons later, this guy called Max Knoll, a physicist, he conducted a study where he electrically stimulated the brains of over thousands of participants, and he got similar sort of patterns. And you can see there's some similarities between the two groups. So this points towards this: are these hallucinations, do they have a origin? Is there a spatial symmetry going on at the back of our head that causes this? There were also this study in the 60s where they gave LSD to blind people. So people who are congenitally blind, meaning blind from birth without a visual cortex, they didn't see anything. But people who were blind and had some early visual experience and an intact visual cortex, they did see hallucinations and pattern formation. So this points towards there being an origin at the back of the head. So the first study to sort of look at this was the study by Tutel et al., where they made this macaque monkey look at this stimulus for around 20 minutes, injected the monkey with radioactive dye, and then later they stained the occipital cortex. And you can see there is this pretty remarkable symmetry between these two patterns. And this is the first sort of study to show that there's this mapping going on between the retina and the cortex. This is called the retinotopic map. And similar sort of studies have been done in humans with different stimuli that correlated with different stripe sort of activity. So there's this sort of spatial organization between the retina and the cortex, which is preserved, right? So what we see out here is being mapped here, and what's being mapped here is also being projected out under hallucinations. So what we think is happening is there's spontaneous activity at the back of our heads when we take psychedelics, which through this map is being projected outwards. And not too long ago, we simulated a hallucination. So this is different to a psychedelic hallucination, but what might be happening there is when you first look at this stimuli in your visual field, you're simulating a group of neurons called orientation neurons, which are responsible for detecting edges and angles. And so these neurons start lighting up, and these neurons normally pack together. If they detect similar edges and angles, they pack together and form what is known as a cortical column. So it's the next functional unit. And around 100 of these neurons make up a column. And whether you're dreaming, whether you're seeing an object out there, or whether you're hallucinating, these columns light up and make sense of your visual world. And so in this case, these blue patterns light up, and together they form a certain pattern in the back of your head, which through the map is being projected outwards, and then you saw those sort of distortions earlier. Similarly, we have this mapping with psychedelics, but the way in which spontaneous activity is formed is much different. You're not looking out there and simulating hallucination. It's happening over here. So how does this happen under psychedelics? Yesterday, Leo gave a talk on psychedelic diffusion, which was at the societal level. We're going to hone in and look at this diffusion at the cellular level. So Alan Turing in 1952 was interested in animal patterns and patterns in nature in general. Why are they so symmetric and how are they preserved? And he came up with this model called a reaction diffusion model, where there is an activator which promotes a biological feature, an inhibitor which inhibits it, and then there's this diffusion-driven instability that sort of leads to pattern formation. So in our case, we have an excitatory neuron, which acts as the activator, an inhibitory neuron that acts as an inhibitor, and together these two neurons interact. So for those of you that don't know, an excitatory neuron drives information, spreads information, an inhibitory neuron suppresses the spread, acts as the brakes. And together these two neurons interact and produce a pattern. So for my PhD, I've been working on this particular type of model called the Gray-Scott model, which consists of these equations. Don't be intimidated, I'm just showing it to you for context. So when we solve this, we get a map like this. So essentially, it's parameter space. You can think of it as a coordinate system where regions in the white area don't form patterns, whereas if you move to the green Goldilocks region, that's where all of the magic happens. So to explain it, maybe give you an analogy, you can think of X and Y as control parameters, like the weight. And these control parameters, they will say stable in a certain region. And as you slowly increase this weight, the XY parameters, you get this buckling effect, right? So in this weight example, the beam buckles, but within this model, we get pattern formation. So past that line, that threshold, is when we start seeing patterns, this emergent phenomena. If that still doesn't make sense, so here, in the no pattern region, we get nothing, right? It's homogeneous. These neurons are uniform, so nothing is forming. As you move towards this bit here, now you see the stable patterns start emerging. So yeah, so firstly, there's this Goldilocks region that drives pattern formation. There's also this EI balance, the balance between excitatory neurons and inhibitory neurons seems to make these patterns more intricate and richer, right? So say under normal conditions, this EI balance is fairly, normal. There's nothing going on. You're seeing things as normal. Your visual field has order to it. That's fine. Then as you start moving to this green region and slightly increase the ratio of excitation, you see that this localized activity starts to spread a bit more. Inhibitory neurons are still working, doing their thing, but not as efficiently as before. And you see localized clusters under this smaller EI ratio. As you start increasing this ratio, you see that excitation starts to spread more freely. Inhibition has less reign on these neurons, and then these columns start interacting in more dynamic ways. And we see these more intricate patterns form as we increase this ratio. Again, if that doesn't make sense, so these are 3 coordinates in this parameter space, and all we did is vary the ratio of excitation and inhibition. So as you'll see, as we move and increase this ratio, pattern formation starts to get more global, spatially coherent, and much more organized from being local clusters of activity. So what's next? So now wrapping it all up together, so what's happening under the psychedelic state? So we know that psychedelics bind to 5-HT2A receptors in the brain, and it's pretty widespread. They're partial agonists or agonists at these receptors. And in particular, these receptors are highly expressed at the V1, primary visual cortex, where we think this pattern formation happens. So as you can see, it's very red over there. So now what's happening when we take psychedelics? Let's take LSD, for example. It binds to this serotonin receptor, and then at the cellular and circuit level, it causes different changes. At the cellular and circuit level, we get psychedelics binding to excitatory pyramidal neurons. So this is one of two conditions that are needed for this reaction diffusion model. But psychedelics also bind to inhibitory neurons, which isn't talked about as much. Around 25% of inhibitory neurons have 5-HT2A receptors, so psychedelics also bind to these neurons. And so together, this creates the condition needed for this reaction diffusion, right? So at the cellular and circuit level, we have this sort of mechanism happening. As we shift towards the network level, for those of you that don't know, we have these brain waves, these electrical signals, and they can literally be transformed to 5 bands. One of this band is the alpha band. And alpha band, if you were to close your eyes now, this alpha band would go up, it would shoot up. And you could think of this alpha waves as a sensory bouncer. So under normal conditions, this bouncer is doing their job, it's controlling the flow of sensory information, and it restricts this sensory information from going to the VIP section of the brain where information gets processed to conscious awareness. Under psychedelics, the bouncer is off duty. There's no one controlling what information gets in, and the filter comes out. There's an influx of sensory information, even through internal imagery like pattern formation. And Tobias will speak more about this in his talk, this filter, what happens then. So one of the most consistent findings at the level of these alpha waves is that they decrease, and they correlate with the intensity of visual imagery. So this has been seen across ayahuasca, psilocybin, LSD, DMT. So there's this decrease in alpha. So we'll first focus at the cellular and circuit level, what's happening, bringing it all together. Then I'll talk about the relevance of alpha oscillations afterwards. So bringing it all together. Under normal conditions, we are in this white region. Nothing's happening. EI balance is fairly stable. Your cortical columns, you can see, regions with stronger synaptic connections are active, whereas everything else is quiet. So this probably would map onto, I don't know, an object out there in the world. But because it's in this normal region, we don't get pattern formation, right? Then, say, a low to medium dose of psychedelics, we see the shift of this EI balance more towards excitation. As we go there, now we can see columns start communicating in ways that they initially didn't communicate. So columns with weaker synapses are now activating. Inhibition is still present, but it's not able to rein in the control of information now. And because we've moved into this green region, at the visual cortex, we might see something, patterns of activity at the back of the brain, which then projects onto a pattern like this. So this is at a low dose, so these patterns are not as intricate or rich. But now, as we shift towards a higher dose, EI balance is now more towards that side. And now these columns are going crazy. They're talking to each other in ways that they initially, under normal conditions, wouldn't. And now we see the formation of more intricate, spatially coherent organization of these patterns under high dose of psychedelics. And so alpha goes down as well. So for normal, that would be high alpha, which under a low dose of psychedelics would start to go down even further under a high dose. So what is driving this richer patterns at high dose? Particularly DMT seems to show these intricate geometrical patterns, right? In the model we used, we kept the inhibitory ratio constant and just incrementally increase excitation. And as we've done this, you can see it gets it gets richer. So in psychedelics, what's going on when we take psychedelics, as in, I don't think these have been quantified before, this EI balance. So when it goes from a low dose to a high dose, is there an increase in excitation, a decrease in inhibition, or are both of these things happening simultaneously? My hunch is on the middle one. And it would be cool, because if we quantified this, we'd be able to understand, okay, can we feed this back into the model and then see if these similar sort of pattern-forming mechanisms happen under psychedelics and not just in a model. And we could also kind of understand these alpha oscillations better. Like I mentioned earlier on, these alpha oscillations act as this inhibitory control. They rein the sensory information in. And this seems to go down under psychedelics. And maybe by quantifying this EI balance at the level of the visual cortex, we might be able to help inform these alpha oscillations. So, of course, MAP is never the territory. There's around 23 inhibitory neurons, 19 excitatory neurons. We just looked at 2 generic neurons. Psychedelics also bind to 5-HT1B receptors, dopamine receptors. There's probably a bunch of different signaling cascades happening downstream that influence pattern formation. And phenomenological reports of DMT patterns being 4-dimensional or beyond dimensionality doesn't seem to fit this model. And if you're interested in an alternative take on the origin of these hallucinations, this paper by David Luke is really cool. He looks at anomalous experiences, people who are blind and have these experiences and have visual experiences. So it's a framework that goes beyond the materialist reductionist perspective, which my talk is kind of based around. So yeah, it's a cool paper. To summarize, psychedelics affect excitatory pyramidal neurons and inhibitory interneurons at the visual cortex. This imbalance between excitation and inhibition drives spontaneous pattern formation, and this can be understood through reaction diffusion models. Patterns formed at V1 or the primary visual cortex are projected to the visual field through this mapping that happens between what we see here and what's mapped here. And at high doses, psychedelics produce richer patterns than at lower doses. And this might be moderated by this EO ratio. We don't know. And yes, this is a reductionist take on it, but I think that it is pretty remarkable that if this is how we do hallucinate, that nature has designed us to have this hardwired kaleidoscope, which I think is fascinating. We get to experience that under psychedelics or altered states. And Oliver Sacks, he says it better. It is in this sense the geometric hallucinations allow us to experience in ourselves not only a universal of neural functioning, but a universal of nature itself. So these are my amazing supervisors and colleagues who've directly or indirectly contributed. Yeah, thank you.